Good morning. I am Krishna Kumar from Krishna's classroom. We continue with our discussion on Riemann Stieltjes Integral. Next, we start with vector valued functions and their integration. This is a straightforward generalization of what we have done with some variations corresponding to that. And certainly this has some kind of significance in the field of dynamics as well as differential geometry. So let us have a look at all those aspects. But before that, we introduce certain notations which are essential for our discussion. So we take Rk is R cross usual vector space structure over the field R. Now dimension of Rk is this is something very basic about it. Now a vector in Rk can be written as x belongs to Rk. Then x is defined by xk with respect to the standard basis. Okay. We also introduce a norm. Norm is the usual L2 norm. Let me put 2 here, defined as therefore it's a metric space. So that's about the space in which we work. We have been all the time working in R, that is k equal to 1. Of course, k is a positive. Here I'll write finite dimensional vector space. It's a finite dimensional non-linear space, and it is a therefore it's a metric space with the usual metric. So everything is one. So it's a space in which we can very comfortably work with all these ingredients available to us. Now we are interested in working on the following. So we define by let f bar be a map from on that Stieltjes is a map from interval okay. So we shall write F bar T where each Fi is a real value function. Of course, T belongs to A. Now we take a monotonically increasing function on the interval A. So let alpha be a monotonic on AB. Like the alpha that we used in the Riemann Stieltjes integral discussed earlier. Then we can have the following definition. Then we define the following definition. We write F bar belongs to Riemann Stieltjes integral with respect to alpha if and only if Fj belongs to R alpha and in such a case integral is defined as the vector because you know that f1 integral f1 d alpha, f2 d alpha, etc. integral fk d alpha, they are all defined because we are assuming fj belongs to R alpha. Therefore, this essentially belongs to R2. Therefore, the integral mapping from R alpha into R2. So I think let me put a notation. Then one can easily see that over R is in fact an infinite dimensional vector space that you have. That means if you take two functions from R tilde alpha, say f tilde and g tilde, then their sum is in R tilde alpha and a scalar multiple of that is in R tilde alpha. So that is one of the simple results that one can prove exactly as we did in the other case. So you see that what you are using is that each Fi is R alpha. So it is on the strength of that we are going to work on that. So all the results there can be made use of. So this you can write a proof. Further, one can prove that if C belongs to R, C belongs to the interval AB. I can split it. Then what we have is integral A to B f tilde d alpha equal to integral A to C f tilde one can split the interval, I mean integral over the interval A to C and then C to B. Now this we have already seen for scalar valued functions. Just use that result to get this result. So once again you supply it. So wherever I put a proof with a question mark, it is up to you to work it out. It's a good exercise to learn the art of writing proofs. Further, now, moreover, if and G alpha 2, where alpha 1 and alpha 2 are two monotonically increasing functions in the same status of alpha, then alpha 1 plus alpha 2 is monotonically increasing, and r tilde alpha 1 plus alpha 2 f bar belongs to that class, and where the real number basically. So all these results can be proved straight away from the proof, corresponding proof of just real valued functions, and apply that to each one of these f1, f2, etc. fk, because that's given. All this is right. This one is a good exercise. Okay. Now further, one can prove the following here. One can prove the following. And just take out all these things. I hope you want to be printed in your mind. So, let me say this. Monotonically and is differentiable with alpha derivative and f bar is a bounded RK value function quantity then integral a to b f bar b alpha equal to integral a to b f bar alpha derivative of x dx. That is, it can just be the Riemann Stieltjes integral. It's the form of a Riemann integral for the vector value function. This is again analogous to the theorem that we have proved earlier. Now, just a word about boundedness of it. F is said to be bounded if there exists. Okay. Some f here And this is of course if and only if each bounded function. Therefore, all that we need to assume is that each one of fi is bounded. So that is just a remark. Also, so prove this. So prove this theorem. That's quite easy. Also, we have the following here. Let is Riemann integral over AC for E less than or equal to x less than or equal to G put F bar x is the definition integral a to x then f bar is continuous already. Furthermore, if f bar is continuous at x naught belonging to AB, then f bar is differentiable at x naught and f bar prime at x naught equal to now one word about f bar we call for a vector value function f bar which is defined as f bar prime is defined as f1 derivative, f2 derivative, derivative. So that is just a routine thing that you are all familiar with, the natural thing about the derivative of a vector value function. Because there is a reference to that coming in the class. So I am just explaining it out if you have not seen it. So that's okay. Now we can also have the fundamental theorem of calculus for vector valued functions. Theorem of calculus for vector value functions. Theorem. F bar belongs to is Riemann integral over AB. F. Then we have integral A to B F bar T dt equal to this again the proof just uses the application of fundamental theorem of calculus to each one of the component functions. Okay? Because you can see that if f is a vector valued function, then capital F bar is equal to capital F1, capital F2, etc. capital Fk. Then you can connect Fj, capital Fj with small fj, which is the jth component of small f bar. So apply the theorem for that. Okay, so from that you get it. So we don't really go into the proof of that. They are all just routine what is called exploration, assuming the corresponding results for R value functions. Okay. Now we prove one theorem in this case, and which has some slightly different statement from what we have seen earlier, because we are working in the vector valued in a vector space corresponding to proposition. So we state and prove the next theorem. If f bar maps the interval AB to Rq, and if f bar alpha for some monotonically increasing alpha so what I assumed is this F bar maps AB to RK, and if F bar belongs to R alpha for some monotonically increasing alpha on AB, then norm F belongs to R alpha and we have norm of integral A to B F bar B alpha. So two norm values are we have defined earlier. This is less than or equal to integral A to B so this is a scalar valued function. This is a scalar valued function. Norm of F bar is a scalar valued function. And you can easily see that norm F bar is F1 square plus F2 square plus etc. Fk square, the whole thing to the power half. Okay, so that will right work on. Because that norm is involved, we are trying to work out a proof of this. Otherwise, I'll write down the proof is very fine. Let K real valued functions is defined by now we know that F5, they are all real valued functions. F5 belongs to R alpha implies F5 square belongs to R. This we have proven. And that implies further the finite sum of Riemann integrable functions with respect to alpha is again Riemann integrable. Therefore, you have I equal to 1 to K F5 square belongs to R. So we have reached up to this one, but what we need is the power half. Okay. Now for that, one little argument that you will make, which will immediately give you. Look at the function. See, x square is a something like gx equal to x square. Say is a continuous function of x and hence square root function is continuous on the interval 0 to 10. Some number for every real n. You can draw the graph of x to the power of the square root function and then convince yourself that it is in fact, or one can prove it actually also. Therefore, what you have to do, you have to compose this square root function with f1 square plus f2 square plus etc. fk square. That will give you f1 square plus f2 square plus etc. fk square to the power half. Hence, what we have is that norm of f this is that composition of, you have a continuous function, you have a Riemann integrable function, then the composition of these two functions is a Riemann integrable. Just use the composition. So that is there. Therefore, you have this Riemann integrable with respect to alpha. Now we have to prove the validity of this inequality. So this we have already proved. So for that so to prove the inequality, in this statement, we introduce some notations. So put y bar vector as yk. It's a vector in R. And further, the component yj equal to integral fj dr. Then y this is what. Now let us work out this. We work out mod y square. Mod y square is essentially y1 square okay. Now this I rewrite in the following form. Sigma j equal to 1 to k. I write 1 yj as it is, and the other one I give the definition here. Integral a to b now this I can write as sigma, or again because this is a constant I can just pull it out and I can write this as, it's also finite sum, so I can interchange the summation with the integration, and what I can write is this. This is we apply Schwarz inequality. Then we have sigma this is less than or equal to norm this is that. Okay, so this is for T belonging to T. And this implies norm of this is equal to, this is less than or equal to norm of y bar square into integral a to b this is coming from the following. Or real numbers. This is less than or equal to so we are just using this. Okay. So there are two cases where if norm y bar is equal to 0, then the inequality is trivial. What is the inequality? The inequality is then integral a to b f bar b alpha this is clear. Okay, because what happens is that this is 0 and it's also 0, so you have equality there. So if norm of y is not equal to 0, if norm of y is not equal to 0, we can divide both sides by norm of y. If norm of y not equal to 0, then we can divide both sides by norm y to and this is, of course, what you have is this is equal to integral a to b this to here, this to here, this to consistent notation, and this to. Okay, so I get yeah. So this is what. So that completes the proof of this result.